Hi, everybody. Welcome back to our final installment of this course on asymptotics and perturbation methods. For our grand finale, I'd like to show you a new method, actually, a new technique in perturbation theory, new on the order of like 25 years old. Still, that does feel kind of new since a lot of this subject is classical, from 100 years ago. So, the method goes by the name of renormalization. It's a term that's been used in various contexts before. You're probably aware that a Nobel Prize was awarded for a renormalization group in physics, in understanding of critical phenomena, in statistical mechanics, trying to understand phase transitions and the critical exponents that are seen there. But then renormalization was famously used by Mitchell Feigenbaum to understand the period doubling route to chaos. And various Fields medals have been awarded in the past few years for putting Feigenbaum's work on a firmer mathematical foundation. Anyway, so renormalization is a hot and very powerful technique. Pioneered, I think, really maybe first in particle physics, later in statistical physics, still later into dynamical systems, and later still into our topic of singularly perturbed differential equations, either ordinary or partial differential equations. The whole method is still, I have to admit, very unfamiliar to me and also very murky. But fascinating, and I wanted to learn a bit about it. And so I want to tell you what I have figured out, which isn't that much. All right. You'll see, I'll post a bunch of papers in our course files you can look at. You'll see different people trying to explain these ideas in various ways. So the key work is by Chen, Goldenfeld, and Oono. And so I'll include their paper from 1996. Then once their work came out, various people tried their own way of explaining it. So the dynamical systems people tried to recast the physics language into normal form theory, a standard technique in dynamics. There's also ways of thinking about it just using computer algebra, which I don't find particularly very enlightening. To me, the clear, and I haven't seen a very, very good pedagogical article about it. There are some, to me, they haven't been that helpful. I thought one of the best articles is the one I'm going to discuss today, which uses geometrical ideas. And I found it pretty visual and relatively easy to interpret. So let me dive in and try to show you what I've got. So why are we making the big fuss? The claim is that renormalization can subsume pretty much every technique we've done in the course. It will include as special cases, WKB, boundary layer theory, multiple scales. They're all unified by this point of view. And there are problems that were historically very hard to solve, or in fact, some are still unsolved, that renormalization seems to be able to solve. So it may be the best method of all once we figure out how it works. All right, and okay, so let me dive in. Sorry for that long preamble, but there is a lot to say. All right, so the method I'd like to show treats renormalization by thinking about a classical idea in geometry called envelopes of families of curves. So as I mentioned, the general idea of applying renormalization to differential equations comes from Chen, Goldenfeld, and Oono. But I'm going to focus on a paper by a Japanese researcher named Kunihiro. In particular, this paper, a geometrical formulation of the renormalization group method. So he says, I'm not positive that this is a male. I don't know my Japanese names so well. So is Teiji a male or female? I'm not sure. But anyway, Kunihiro says, on the basis of the classical theory of envelopes, we formulate renormalization group method for global analysis recently proposed by Goldenfeld et al. It's clarified why the renormalization group equation improves the global nature of functions obtained in the perturbation theory. So you'll see what that means in the course of this discussion. Is the recording on? Good question. Is it? Let's see. I don't know. Is it not? Shit. No, it is. It's flashing. So of course it's on. Okay. God, now I'm embarrassed. I'm swearing on camera. All right. Okay. I think it's on. I'm not going to start over after that long preamble. Okay. So let's get into it. First of all, envelopes. You know, that used to be a standard topic in multivariable calculus. I don't think we teach it anymore. I've taught it once or twice in my career, but since you may not be familiar with how to calculate an envelope of a family of curves, I thought I should just do a basic example. And then we'll tie it to renormalization in a few minutes. All right. So here's a little example of the phenomenon of an envelope and how to calculate it. So think about the question of a family of straight lines, like here's one, of unit length. So think of this as a fixed line segment of unit length, and we're interested in the straight lines of line segments of unit length between their x and y intercepts, say between these 2 points. And then let that sort of slide down, almost like a ladder sliding down a wall, keeping one point in contact with the wall while the bottom slides out. So as you can see, you know, this sort of looks like it's trying to have a bounding curve that's what we mean by this envelope. It's a curve with the property that each of these tangent lines is touching the curve at one point and is tangent to the curve. Is there a curve that has this property that these lines are then the tangent lines to that curve? Doesn't have to, you know, envelopes don't just involve necessarily lines. We'll see more general instances in a few minutes. But for now, you can sort of visualize there's some curve there. And so let me just formalize what I'm talking about. When I say lines of unit length between their intercepts, you could parameterize it like this. Think of this point and this point as the intercepts. And then just by defining this angle in here, I'm going to call it tau to be consistent with Kunihiro's article. This distance would represent cosine of tau. This would be sine of tau. Here's my unit length line segment. And so the intercepts come in here in the denominators as x over cosine tau plus y over sine tau equals 1. That'd be a way of writing in parametric form this family of lines, depending on the parameter tau. So now we're interested in trying to figure out what the envelope of that looks like. And let me jump out to Mathematica for a second to show you how this goes. So I'll share different screen. Let's see. I think it's this one. Yeah, envelopes. All right, so I've written this family of curves, x over, or the family of straight lines actually, x over cosine tau plus y over sine tau equals 1 as a function. Think of it as some function f of x and y and tau. When that function equals 0, then we have a member of this family of straight lines. And so I'm just going to make it possible to graph this easily in Mathematica. I've written it a certain way where I can now manipulate this slider, and you can see, you know, sort of looks like, as I say, this ladder sliding down the wall. Okay, so there's my family of curves. And if I plot several members of that family, then you get a picture that looks like that. And as you can see, it looks like it's sort of trying to have some bounding curve here, that's the envelope that we're looking for. Now, the classical theory, which I'm not going to derive, it is a multivariable calculus topic, tells us how to find envelopes. And so I'll just tell you the prescription without deriving it, which is that you go back to this function that defines the family, f, a function of three variables, x, y, and the parameter tau. And you simultaneously solve where f is equal to 0 and where the partial derivative of f with respect to tau is equal to 0. That's the key condition. And that's a condition that has a counterpart that comes up in the renormalization group arguments. A partial of something with respect to a parameter equaling 0 is a renormalization condition we'll see later on. And it's often presented kind of mysteriously. And I liked it in this envelope context as just a classical envelope condition. Partial f with respect to tau 0 and f equals 0. If you solve those two simultaneously, I'll show you in a minute, that will give you a red curve that I'm showing here that turns out to be the envelope. And that curve is defined by this equation, 1 minus x to the 2/3 power. So y is equal to 1 minus x to the 2/3 all to the 3/2. It turns out, we'll see that in a minute. And that ends up giving you the envelope. It's actually a famous curve. It's called an asteroid because if you graph it in all four quadrants, it looks like a star. So the word aster, like star, or disaster for bad stars, or astronomy. Anyway, that root, astro for star, this curve is an asteroid. It's got parametric equations, x equals cosine t cubed, y equals sine t cubed. So let's see where that came from. Let me jump out of there now and back to my notes. Nope, didn't work. Let's try again. Oh, I have to screen share. Okay. Share screen, share iPad. There. Okay. So as I say, I'm going to rewrite the family as f of x, y, tau equals 0. By rewriting this equation, if I cross multiply by the denominators, if I multiply by sine t or sine tau, cosine tau, I can rewrite this equation as this equation here in the box. So that defines my family of lines. And then, as I say, the prescription is to find an envelope, you set f equal to 0, the family condition, and partial with respect to the parameter equals 0. If you do that, I realize it may not be obvious why you're doing that, but if you do that, well, as I say, you can find a derivation in old books on multivariable calculus. I'll show you some in a minute. But anyway, actually, I guess I'm going to show that now. So here I've pasted in for the notes. You can take your time later and read these notes where they do derive that condition. So they do a little example. They get the condition I'm describing down here, where a partial derivative is set equal to 0. Anyway, in our example, that condition, partial f with respect to tau equals 0, turns out to be this equation. And if you then solve it simultaneously with f equals 0, you can derive, it's linear equations in x and y. So it's not that bad. This one's linear in x and y. And the equation for f equals 0 is, of course, also linear in x and y. So though it looks complicated, it's just a pair of simultaneous equations in x and y. So you can solve for them in terms of tau, and you'll end up getting this equation in the box. X is cosine cubed tau, y is sine cubed tau. And so you can see by cosine squared plus sine squared equals 1, that if I take x to the 2/3 power, making this 3 into a 2, and y to the 2/3 power, that x to the 2/3 plus y to the 2/3 is 1. So it sort of looks like the equation for a circle, except instead of x squared, it's x to the 2/3. Anyway, it gives you an asteroid. And so this is the equation for the envelope. And as I showed in the computer, it sort of seems to work. Okay, so that's all I really want to say about envelopes. And with that, I want to now try to connect this to this idea of renormalization and say, what do we mean by renormalization? Maybe before I go into that, I should ask if you would like to ask anything about envelopes at this point.
This is just out of curiosity. Why are they not taught anymore?
Why are they not taught anymore? Don't know. They should be. They're beautiful. And some good professors, I'm sure, do teach them. I don't know. Things go in and out of fashion. You won't find them in many textbooks either. Basically, a lot of neat geometry has been taken out of textbooks. I don't know why. I think it's a really nice topic. And envelopes do come up all over the place in applied math. But yeah, I know in our course at Cornell, we don't teach them. So too bad. We should. Anyway, so as far as our renormalization example, let's see, a comment in the chat. You've seen it in macroeconomics, says Mark. Interesting. Okay, yeah. No, it certainly comes up. I mean, in wave propagation, people often think about the envelope of the modulated amplitude of a wave. It comes up there. It's certainly an important topic. So it should be taught. Anyway, so here to illustrate the idea of renormalization and how it's different from everything we've seen so far, I'm going to go back to one of our model problems that is exactly solvable, but we'll try to solve it with perturbation theory just to illustrate the technique. So it's a second order linear differential equation with constant coefficients, very elementary. And we've seen things like this before when we were studying boundary layer theory or WKB. So it's a boundary value problem. We could write down an exact solution if we want by just solving it with the usual techniques, method of undetermined coefficients. Anyway, you get something that has sort of an outer solution and an inner solution in boundary layer terminology. And we're going to see that the renormalization method recovers this whole thing without any need for matching. That's one of the virtues of the method. You don't have to match. The matching happens automatically, sort of like in WKB, but this is more general because renormalization works also for nonlinear equations, whereas WKB is only for linear ones. So anyway, that's what the exact solution is going to look like. It gives you a feeling for the character of what we should expect. Now, let's try to solve it, pretending we don't know the exact solution with renormalization. So what does this mean? Well, we're going to write out what would, in a boundary layer terminology, be the inner equation. So we'll do what it takes to make this, we have this epsilon in front of our highest derivative. We're going to redefine our x coordinate to get rid of that epsilon in front of the highest derivative so we don't lose it at order 1. And so that's the classic move of looking at an inner equation. So we'll do that. We'll write out the inner equation. Then we'll just naively solve it with regular perturbation theory. And so Goldenfeld and company frequently refer to this as the naive expansion. It's just what you would first think to do if you were using regular perturbation theory. And we know that it's naive from what we've seen throughout the course because it will generate all kinds of secular terms. And, part of our methodology has been to find ways to get rid of those because they mess up our asymptotics. The cool idea in renormalization is we're not scared of those secular terms. We just generate them and we don't worry about their secularity. We will find a way to tame them by renormalizing. But we do go ahead and generate them. Rather than killing off the secular terms, we let them flower and bloom and they guide us in our renormalization. So we're going to renormalize them away later, but we're not scared of them when they come up. So, okay, so let me explain what I'm talking about. We go into the inner region by just changing the variables the usual way. Capital X is X over epsilon. We write Y in terms of the new variable big X as usual. We get an equation that looks like the type of thing we've seen a lot before. Where now notice that the second derivative no longer has an epsilon in front of it, and the epsilon has been shifted over to this side in front of these terms. So nothing's been approximated so far. It's all exact. We just changed X. Okay, then we do a naive regular perturbation assumption for Y and plug it in. And to save writing, let's use prime to mean d by dx. So if we plug that in, then we get our usual sequence of linear equations for the various terms in the regular perturbation series. So we get a Y0 term that, this is not a simple harmonic oscillator, although we've been seeing a lot of those in multiple scales. This has a, rather than Y double prime plus Y, it's Y double prime plus Y prime, right, coming from here. So this is going to have exponentially decaying solutions and a constant at order 1. And then there's an order epsilon equation where the Y0 stuff appears on the right-hand side. We've got the same operator on the left as we had above here. So it all looks very typical for regular perturbation theory. So as I say, so far this looks like just ordinary boundary layer theory. And it's at this point that we start to reason differently. So let me see. I think, is that maybe where I stopped writing? Yeah, it is. Okay. So let's see what to do here. Maybe I'll dive into Mathematica to show you what happens if we, I'm wondering if that's the best idea. Maybe not. Maybe what best thing to do is to just look at the paper by Kunihiro. So let me share that with you. I hope this will all be visible enough. Tell me if it's not big enough. So let's find it. Is it here? Here. Okay. How's that for visibility and readability? Fine. Yeah, okay. All right. Okay. So he begins, I mean, here's the problem that we wrote down. And he's got some boundary conditions. He points out the exact solution that we talked about a minute ago. He sets up the inner equation, just as we did, expands in the power series, and starts generating that sequence of equations. Now, at this point, he does something a little bit strange looking. And he says, we set a boundary condition for Y at some arbitrary point x0. It's weird. It's not a boundary point. It's just some, think of x0 as just some point anywhere in the domain. And I guess, I mean, I'm confused about what's going on at this point. I think what he's doing is, it's like he's saying, if I knew the solution, capital Y, like suppose, I mean, there is some solution to our problem. If we knew what it was, then at some point x0, we could plug in that x0 into our, let's suppose temporarily, we know the function Y and Y0 and all the parts of Y. Then we would get an A0 that could be determined given the x0 that we happen to be evaluating Y at. I mean, we're not really saying anything. We're just saying that if we have some x0, we could in principle calculate y0 at that x0 to get something a0. So what good does this do us? we're going to end up using this x0 kind of like a parameter in an envelope equation. It's almost going to be that here's the basic idea as I understand it at the moment, which I don't trust, but I think what's going on is there's only one solution to this boundary value problem. If we try to express the solution in terms of this arbitrary point x0, the solution can't depend on x0 because the solution doesn't have any, the solution is what it is. It might look like it depends on x0, but it doesn't. In other words, when I take a certain partial derivative with respect to x0, nothing will change. And that's like an envelope condition. So you'll see what I mean. Let me just sort of go through the algebra here. Like, let's just take this for granted. Now, this is the first place I got upset as I was trying to figure this out this morning. And the reason this lecture is so different from the usual is that I haven't actually figured this out. And so I'm winging it. Full disclosure. So for instance, there's a typo immediately at this point. He says that he wants y0 at x0 to be a0, but he writes down a solution that violates that. So what, right? Plug in x equals x0, then you would have e to the 0 power, which is 1. According to what he wrote down here, y0 of x would be a0 minus b0, not a0. Does that matter? I think it doesn't. I think it doesn't matter. I think what's really going on is he doesn't really mean this. He's not really setting y0 to be a0 at some point. What I think he's really doing is, and this part is correct, I think he's saying just solve this y0 equation. It's going to involve we can do it in our heads. What's the solution of y0 double prime plus y0 prime equals 0? Answer, a constant plus a constant times e to the minus x. Okay, that's it, right? It's a very easy equation. A constant plus another constant times e to the minus x. And what he's written here has that form. It's a constant a0, another constant, which rather than just calling it b0, think of it as b0 times this e to the positive x0. That can all be lumped into the prefactor of the e to the minus x term. So this step is correct. He just hasn't actually imposed the side condition that he said he was imposing. But it doesn't really matter, I think. Certainly you can write, if you choose to, the solution of this order 1 equation in this form. There's nothing wrong with that. And it involves an arbitrary number x0, which he's, I think, going to make use of. Right? So would you agree with me that nothing wrong has happened yet? It's not clear why this is any use, but there's nothing wrong, other than that this statement is not really being enforced the way he said it was. But I don't think it matters. Okay, so anyway, he's written the general solution y0 of x in this way, where there's this peculiar x0 entering. And you'll see similar peculiarities in the literature on renormalization in Goldenfeld's papers too. So it seems to be some essential part of what they do. Anyway, nothing wrong so far. Now, how does this help? Well, let's go to the next page. He can then calculate y1. After all, y1 is just defined by, sorry, I've gone too far. Y1 satisfies this differential equation right here, right? It involves the y's. You have to plug in the known solution for y0 that we just wrote down, and then solve for y1. So doing that, he gets this y1 in terms of the previous constants that were called a0 and b0, and it also generates a new constant, c0. But anyway, there it is. So there's a y1. Okay. So lots of constants flying around. And then when if he writes the whole expression for y, meaning, remember, y is y0 plus epsilon y1, right? It's got the leading order plus the epsilon term. If he writes both of them, y0 plus epsilon y1, he's showing that it's of the form a constant minus a constant times an e to the minus x0, and a term that looks secular. It has an epsilon times an x. Although, again, he's using this x0, which is just contributing some constant, epsilon a x0. So there's nothing wrong at this point. It's all good. It's just a funny way of, like here, he's redefined these constants, or probably I should even say renormalized the constants in this way by introducing a in terms of a0, b0, and c0. But if it all looks very mystifying, all that's really going on is the general solution for y involves, we could put it this way, actually. I think maybe this is a clearer way to say things. Well, maybe this is better. If I look at this problem, these two linear differential equations, how many degrees of freedom would I have in solving this? I have a second order equation here that will generate two constants. And when I solve this, I'll generate two more constants, in addition to dragging along the constants from before. So altogether, at this stage, I should have four constants in my solution for y. If I write y is y0 plus epsilon y1, there will be four constants. And you see that on the next page, there are four constants. He's written them in a peculiar way, a, b, x0, and I've already messed up. Where's c? I don't know. I'm confused. I would have thought I needed one more constant for full generality. I thought I was in good shape. I had an a0, a b0, a c0, and an x0.
A and B depend on C as well. If you write them in.
I mean, maybe the point is that A0, wait, sorry, what did you say, Maria? A and B depend on C?
I'm saying that the A and B, they depend on A0, B0, and C0. So implicitly you have three constants, but you just write two of them because there's a fancy trick of writing just two, if you define A and B to be like that.
Well, all right, let me accept your argument, just in the interest of moving along. So anyway, he goes then back to the original variable little x and says, we're getting a solution that looks like a constant, a, another constant. Notice that this, of course, we've got this inner looking term, e to the minus x0 over epsilon. And then this sort of secular looking thing, a times x minus x0. But at this point, he says, now, let's obtain the envelope of these. This is a family of functions where he's thinking of the x0 as kind of like the parameter. So if he takes the envelope of all that, then he does that envelope condition, d of the function with respect to the parameter. Set that equal to 0. When he does that, he ends up deriving equations for A and B that are differential equations with respect to the x0 that they depend on. I mean, A and B really, this is confusing. Are A and, remember, we said earlier, way back here, he said, I choose some interior point x0 that's arbitrary. And if I demand that y, my function y, whatever it is, it evaluates to something a0 that depends on the choice of x0. So all the constants, like a0 and b0, they all depend on the x0. As you slide along and through the interior, the a0 and the b0 would depend on this x0. So in here, although they look like constants, they do depend on the x0. And so here, when he writes this, when he differentiates, he has to remember that A and B and all the rest depend on x0. And so you end up getting expressions, like when you differentiate the A, it's not 0, it's going to give you an A prime. or the prime now means derivative with respect to x0. In other words, he's deriving amplitude equations, we used to call them. These are the slow time, I mean, in multiple scales, these would be the slow time equations. They're, in other fields, they would be called envelope equations. So anyway, we're getting these little equations for A and B, little differential equations, which you can then solve. Here he calls x0, he's just calling it x, because he, at the point of tangency in the envelope, x0 and x are the same thing. So he ends up deriving equations for A of x and B of x that he can solve and gets them. There they are. They're simple exponentials. And then when you plug that back in to this stuff above, here the A and the B are genuine, A bar and B bar, these are genuine constants. So when all that is plugged back in, this is the form of the solution for the envelope, which you'll see involves both something that it looks like an outer solution and something that looks like an inner solution. And they just popped out automatically with no need for matching an inner to an outer over an overlap region. That just happened automatically. So then you can just impose the boundary conditions from the original problem. You can impose a condition at 0 and at 1, and then get these constants A bar and B bar, and they come out to be exactly what you want. The envelope condition gives you the exact solution. In other words, the A bar and B bar, they end up being this denominator that we saw earlier in the exact solution. So in terms of what does this have to do with envelopes, here he's actually showing the envelopes. So what's going on? The thin lines, he says, represent this family of curves. In our earlier example, those were straight lines, but in general, you could have envelopes to a family of curves. So like here, he's showing what we would think of as a secular term coming from the naive expansion. I don't know, can you see it or does it need to be bigger? I mean, if that's too small there in the bottom, right? That's showing A at x0 minus B at x0, exponential e to the minus x0 over epsilon. And then this funny term that came from regular perturbation theory, A at x0 times x minus x0. If you graph those terms for various choices of x0, remember thinking of that as the parameter. If you just slide along for different x0 for various values, 0.2, 0.4, 0.8, you get this family of curves. Here's the one for 0.4, here's the one for 0.2, here's the one for 0.8. And you see that that family has some envelope. And the envelope is what we just calculated. In other words, the envelope of this family of the expressions from the regular perturbation theory is the correct result that obtained by renormalization. So I realize this is mystifying. I'm mystified myself. But anyway, there you go. So let's see if he says more about this example. Well, no, I think that was the end of that one. Let's see. Yeah, I think that's it. So let me see, is there a comment in the chat? Can I post this paper to Canvas? Yes. Should I do it right now, you mean? So you can follow along that way? I could do that. Would that, yeah.
Just at some point. It doesn't.
Oh, well, I certainly will. Yeah, I'm going to include all of these in the page for today's lecture. This one and Goldenfeld and Oono and Chen, and the paper that tries to think about these things with normal forms, I found pretty good, by Tasso Copper and Mark Holzer. So anyway, there's a lot to understand here. But I mean, maybe since I've got this one up, should I just show you a few more examples from his paper? You'll get a flavor how it goes. I realize it's probably hard to follow so fast, but it's the best I can do. So let me show you his earlier examples. Okay, so the paper, I mean, the structure of the paper is, he says, he himself finds the reason why renormalization group can be relevant for global analysis, meaning singular perturbation theory. He says it's kind of obscure. So he tries to find a mathematical explanation for why it works. And so after he reviews the basics of envelope theory, similar to what I tried to do at the beginning, he gives an example of a bunch of, some expressions that then have an envelope to remind you how envelopes look. And then he does a little problem involving a damped linear oscillator as a warm-up. So why don't we just glance at that one? It's a simple harmonic oscillator with damping epsilon, dx dt. So we know what that's going to do. It generates something that looks like a constant, exponential decay on the amplitude, and then a sine function with an altered frequency compared to the unperturbed problem, and then a constant phase. Okay, so that's what the exact solution is. Now, he says, let us blindly try to get the solution in perturbation theory. If you just did a naive perturbation theory, regular perturbation, we saw when we were first doing multiple scales that this will generate secular terms. And that's what led us to create the Poincaré-Lindstedt method, the method of multiple scales, whatever. But here's a different way of handling it. Just plug in the naive perturbation expansion, generate an equation at order 1 and at order all higher orders of epsilon, and solve them. Now, one thing that you'll see people do when you start reading the literature on renormalization is they solve the lowest order equation fully. So like here I have x0 is a0 sine t plus theta 0. That's the general solution for the order 1 equation. But then when they do the next order, like suppose we were doing x1, here's the equation for x1. x1 double dot plus x1 is, and then I substitute in minus x0 dot, so that gives me this. When they solve for x1, they only write down the particular solution. They don't bother writing down the homogeneous solution. That's sort of customary in this part of renormalization. And why not? Why can they get away with only writing down the particular solution? The argument that they always make is that if you did write down the homogeneous solution, it would end up just basically changing this constant A0 and this constant theta 0, which people think of as kind of depending on epsilon. So in other words, if the A0 and the theta 0 depended on epsilon, and you expanded everything in powers of epsilon, all that would do is it would just generate the homogeneous solutions at all higher orders. All the time, you've captured the time dependence already. So why keep capturing it at all the higher orders? So they just skip it. And it works. It's general enough to just look for the particular solution. So you'll see here, here's a particular solution for x1, here's a particular solution for x2, and so on. And notice that they have secular behavior. Like if we were interested in what's happening at long time, these look bad because this says t minus t0, and this one says t minus t0 squared. And here's a t minus t0 cosine, right? These things would start, they look like they're blowing up at long time. Of course, they have epsilons in front of them, so they're not really blowing up. But in traditional perturbation theory, when you're looking for asymptotic expansions, these are considered very problematic terms. Nevertheless, in renormalization, you just crank them out. And so let's see what else Kunihiro says. So he says, although we intentionally omitted the unperturbed solution from Xn, he means the homogeneous solution. We intentionally omitted it. Yeah, it's fine. He says, actually, this prescription is not adopted in reference 1. So apparently Goldenfeld, Oono, and Chen include the homogeneous solution, but you don't need to. And as he says, subsequent calculations are simplified if you just omit it. Okay, but anyway, the secular terms have appeared. they're absent in the exact solution, which we know has exponentially damped amplitude, not something growing in time. So traditional thinking would be that this whole approach is invalid if t is far from t0, meaning that these terms are getting big. Okay, nevertheless, this is what the whole thing looks like. And so then you write out the whole solution as order 1 plus order epsilon plus order epsilon squared. And again, traditional thinking would say that the ordering of these terms, it's supposed to be that this term dominates this term, which is formally order epsilon, which will dominate this term, which looks like epsilon squared. All of that is okay as long as t is much smaller than 1 over epsilon, right? That's what we've said in the past. But we would like a result that works out to timescales of order 1 over epsilon. And that's why we invented the methods that we had. Well, this method can accommodate all of that too. Watch how it does it. Instead of what we did, the way that Kunihiro argues it is, here's a family of curves. Look, I mean, it's x, it depends on a parameter, t0, this mysterious intermediate time that plays the role of a parameter. So, okay, I've got a family of curves that depends on a parameter, t0. They're all solutions of the differential equation that work up to order epsilon cubed. I don't care about secularity, that doesn't scare me. I have a family of solutions. They depend on a parameter. Well, now I look at their envelope. So he says, let us find a solution, a function, xe, e for envelope, that represents the envelope of this family of curves. So according to the envelope condition, you're supposed to take partial of the family with respect to the parameter t0. So he does that. And he says it will be shown that the solution for the envelope satisfies the original differential equation uniformly for all times. I think he means for all times up to order 1 over epsilon to the 4th. I mean, you can stretch it out very far. But this is the key condition, this envelope condition. And so he says our equation 3.7 is in the same form as what Goldenfeld and company derived by renormalization arguments from physics. So, but in Kunihiro's formulation, it's an envelope condition. Okay, maybe I should pause there. And are you following this calculation? More or less? I mean, the philosophy, it'll be better when you do it slowly yourself. Do you want to ask anything, or should I just finish this off? Okay. Well, so let's see. We have this condition. He says, now we just have to get rid of this t0 because after all, it's just this meaningless parameter. So let's see what happens on the next page. Well, where is this now? Oh, okay. So I guess what he does, he says it becomes complicated, but you can greatly reduce the complexity by assuming that this parameter t0 coincides with the point of tangency, namely, you set t0 equal to t. So, and he says, we remark here the meaning of setting t0 equals t is not clearly explained in Goldenfeld, Chen, and Oono. Whereas for him, he thinks it is clear. It's the condition that you would impose for, it's the condition that each member of the family of curves has to be tangent to the envelope. That's what it boils down to. You'll see when you read his envelope discussion that that's what that means. So what's equations 3.7 and 3.9? Where are they? 3.7 and 3.9. So 3.7, I think, is this one. So let's see if we can do it. I mean, I could try to do it quickly in Mathematica, but I think what we're supposed to do is we take this expression, this messy thing, easy enough to generate in Mathematica, take this expression, take its partial with respect to t0, generate a big mess, right? Because you have, I mean, it's actually not so terrible. The t minus t0 is only appearing here. But you have to keep in mind that A also depends on t0. Like remember in the last problem, I said that the A depended on the arbitrary place x0. Here you have to think of the A0 as depending on t0. It's where you are as you're sliding along in this intermediate place. So when you differentiate this in this equation, you got to keep in mind A0 depends on t0, and so does this secular term t minus t0, and this term t minus t0 squared. But this stuff, like t and, oh, also theta 0 depends on t0, right? So a lot of things will depend on t0. T does not. T is a separate conceptual thing from t0. But everything else does depend on t0. So when you take this derivative, you get a bunch of terms. And then at the end, you set t equals t0. And that will knock out a lot of terms. And so what you end up with is just equations for these quantities like A0 and theta 0. These come out to be the resulting differential equations, which you'll recognize are basically the counterparts of the slow time equations in the method of multiple scales. So the thing is, though, that we didn't really have to do anything clever. I mean, this is another virtue of the renormalization group method. You never have to be clever about what perturbation ansatz to assume. You just assume the most naive ansatz, the regular perturbation theory. If there are confusing terms, for instance, logarithmic terms, we never even did logarithms in this course. Sometimes instead of just epsilon and epsilon squared, you can have log epsilon or epsilon log epsilon. This method finds those terms automatically. It turns out. I could show you another paper that demonstrates that. But anyway, meanwhile, back to this problem, you just solve for the A0 and the theta 0 in terms of genuine constants and things that depend on time. And then you end up getting this beautiful solution here, 312, which has exponential decay on the amplitude like it should, and it has a corrected frequency on the sine function like it should. And it's a very good approximation to the exact solution, which involved a square root. To lowest order, this is capturing that square root up to order epsilon to the fourth. And so Kunihiro makes the point that this resulting envelope function, it is approximate. I mean, it's not getting the frequency exact. It is approximate, but it's globally valid in the sense that it's working over a very long range of times. And it's also capturing the right qualitative behavior of exponential damping and altered frequency. So he says the perturbation, the regular perturbation arguments, which were only giving you locally correct results, have now been kind of globalized. They've been improved by this renormalization procedure. So anyway, I will post this. You can definitely take a look. I think while I'm at it, let me just jump out. Since I mentioned logarithms, I'll just show you one other thing. It's probably incomprehensible, but hopefully it will stimulate you to look at the papers on your own. So let me jump out of here to one more paper. I'll also post this one for you. Where do I want to go? I think I want to go here and here and here. And renormalization. So it's this paper. This is a topic we never even got to in the course, which is this concept of logarithmic switchback terms. This is where you're doing a perturbation calculation and you thought you were fine with terms of order epsilon and epsilon squared. And at some point you realize, oh my God, this isn't working. And then you realize it's because there was a term at order log epsilon, which is in between order 1 and order epsilon, or order 1 over epsilon. I'm sorry. I mean, log epsilon will be singular, but it's not as singular as 1 over epsilon. So then you switch back, meaning you go back and repair it by putting in some logarithmic terms manually. That was how people used to do it in the method of multiple scales. And so they call it logarithmic switchback behavior. And it was a nightmare. And you had to be a real like magician to do this stuff. It was a black art. Whereas in this technique with renormalization, the logarithmic switchback terms just pop out on their own. So this paper shows an example. I mean, they're showing here an example of such a thing. You know, like you might have an expansion that looks like a U0 plus an epsilon log epsilon U tilde plus an epsilon term. This is a thing you wouldn't have expected normally, but sometimes it's there. So here's how you can see that without being clever. They give a little example. I mean, this paper is really nice, actually. They make the point of view, they have this point of view, this commutative diagram. It feels like we're doing pure math. They say you can think about perturbation theory and renormalization two different ways. You could start with a vector field, do normal form theory to simplify it and get a simplified vector field. That's a traditional method for solving perturbative problems in dynamical systems, normal form theory. You can go that way. Or if you're a renormalizer, you can go this way around the top and get the same result. So the three steps are, you do RG1, renormalization group step 1, which is do a naive perturbation expansion with regular perturbation theory. S means we're living in the world of solutions, functions of time, rather than in the world of differential equations and vector fields. In other words, rather than transforming the differential equation, which is what normal form theory does, you transform the solution to the differential equation by changing coordinates. So anyway, they say here you generate a solution by doing naive perturbation theory, then you change coordinates in a certain clever way. This is where that envelope condition basically comes in. That's their point of view. They don't think of it as envelopes. They think of it as what in the jargon is called a near identity change of coordinates. So they change coordinates up here, and then they come down by solving the equations again and end up getting the answer. So just to show you what that looks like, here's a little example. I don't know if this is visible. This equation looks fairly harmless. A second order differential equation. It's exactly solvable. It has some boundary conditions. Y0 is 0, Y1 is 2. It turns out this logarithmic switchback phenomenon occurs in this differential equation. And so they show how to analyze it in this section of their paper. It's, I guess, an example due to Eckhouse. So what do they do? Here's the problem we're interested in. This turns out to be the exact solution. It's got these funny logarithmic terms with lots of log epsilon stuff in it. But suppose we didn't know that. Well, you then just go to the inner region. That is, rather than calling X over epsilon capital X, because they're dynamical systems theorists, they call it T. So they write an inner equation in terms of a variable T. They convert the differential equation into this. It's got boundary conditions, one boundary condition at 0, 1 at time. It used to be at X equals 1, so now it's at time 1 over epsilon. Anyway, this is the full problem. They do the naive perturbation assumption for Y, plug it in, you get a Y0 equation. They solve for the Y0 in a general manner, and they get this solution for Y0. Actually, I found this paper much clearer than Kunihiro in the treatment of the constants. I thought Kunihiro kind of made a mess of the constants as far as I could tell. But these guys just solve for the constants. They just have Y0 at some arbitrary point T0. See, they again do that move. They have this parameter T0. They call it an arbitrary initial value T0, but it's not really initial in the sense of the initial value of the problem. It's just an intermediate point. It's just some place where you evaluate Y. So if I knew Y0 at some specified T0, the general solution would be in terms of that specified place, something like this, which, because these are easy equations to solve at order 1. So they just get something, and the logarithm has popped up already at order 1, but that wasn't hard. It just was a relatively easy equation to solve by separation of variables. So they got the y0. Then they go to the order epsilon equation. They have something for y1 dot and z1 dot in terms of they had to plug in earlier information from y0 and z0, creating this term, the 1 over 1 plus t. Then they can solve for the y1 equation. They say we omit the details. I assume you would just do it in Mathematica or whatever. And they get this expression, which is all of y. It's a y0. It's got an epsilon y1, and it's this expression. Similar to what we had before. So we've now just finished the naive perturbation expansion. They point out, it turns out there are no higher order terms. Anyway, I'm probably going too fast. It's probably hopeless. But anyway, they, just to finish, they do this, the second step, this what I was calling the change of coordinates, the near identity change of coordinates, by introducing some kind of new variables, capital Y and capital Z, in such a way that they can clean up as many terms as possible. I'm sorry, I'm sure this is too fast. Anyway, so you'll just have to read it, but they end up getting a nice choice that gives them a new expression here for the y in terms of these new variables, the capital lettered variables. And finally, they can apply the renormalization or envelope condition, the d with respect to t0 equals 0 condition, which like I say, in the literature, that is the most baffling condition. Kunihiro, we saw, thinks of it as an envelope condition. These authors say it a different way. They regard it as an invariance condition. They put it this way: the integration constants depend on t0 in such a way that the solution itself remains invariant as t0 changes. Maybe you like that way of saying it. The solution doesn't know what arbitrary t0 you picked. The solution is the solution. It doesn't have any t0 in it. It just has t and epsilon. So t0 is a make-believe thing. So the answer cannot possibly depend on t0. And yet we see all these formulas with t0s in them. So everything has to have 0 partial derivative with respect to t0. And if you, it's a cool point of view. That's the renormalization vision. And if you do that, you end up getting equations for how the y0 and z0 depend on t0. And those are the slow time or the slow evolution equations, which can then just be solved. Like they say, these are the RG equations, also known as the amplitude or slow time equations. They represent the simplest form in which the system can be put. So then they can solve them, because now that they're relatively simple, everything can be solved. They get the exact solutions. And when they put everything back together, they end up getting the exact solution to the original problem, including with this logarithmic stuff in it. And it didn't need to be guessed. It just pops out. So Goldenfeld has used this kind of stuff to solve some very important longstanding problems in fluid dynamics, like for the flow, the drag on a sphere, if you have flow going past a sphere at low Reynolds number. That's a problem that has bothered people for many, many decades, and it has a lot of mysterious perturbative aspects to it. And that was the kind of thing that led to the invention of these techniques in the first place. So maybe I'll post a link to that paper as well. Anyway, all right. I realize this is a very bizarre lecture, maybe totally incomprehensible, but I hope it's at least made you feel excited to learn about renormalization, which I do think is kind of the most exciting thing on the horizon in asymptotics and perturbation theory today. So maybe that's a good place to end the course. Thanks a lot for your attention and for sticking with me through all these lectures, and hope to see you again. All right, ciao, ciao.